Okay, so we divided, and then we saw what was left, right? And so we had this little x like chilling out here because he was the whole factor, right? He was the whole factor that resulted from my polynomial division. And then what's this circle part?
The horrifying reminder.
The horrifying remainder? Oh dear, that's bad. The horrifying remainder, okay. So the horrifying remainder, what did we do so far? We took the denominator and we factored him, right? Mm-hmm. Why did I have it x plus 1, and x plus 1 squared?
I actually didn't know that. I was going to ask you the class.
That's a good question. Why?
I have a question. Like, why is it like x plus 1 and x plus 1 squared? Like,
why is it?
The x and x plus 1 makes sense because you have x and x plus 1.
But why is x plus 1 squared?
Or x and x plus 1 squared.
Well, here's the question.
Why do you have the extra x plus 1?
If I'm trying to think of all the different pieces that could have resulted or could have combined to make this function right here, this remainder, remember we're forgetting the little x, right? If I was trying to look at the over x and the over x plus 1. Now, if I wasn't to write this piece, okay, if I wasn't to write him, these two could possibly combine to make that, right? However, I have x plus 1 squared. Now, I could do bx plus 1 plus cx plus 1, but they're the same thing, so I could just put it together and make it one number. So I said, okay, there could be two separate x plus 1s, but why not just put those together in a common denominator? They wouldn't be separate, they would be together. But then that also begs the question of, well, hold on. Would it have been possible to have a piece with x plus 1 squared? Yeah. Because I could multiply this one, so I'm going to take away this line for a second. We're trying to think of what are the possible pieces that could have combined. If I can get rid of this line, there he goes. Okay. He could multiply by x over x, right? And he would be a part of that common denominator. He could multiply by x times x plus 1. And he could be a part of that denominator. And he could be times x plus 1 squared. So it's like these x plus 1 and x plus 1 squared are the different terms that could be multiplied. It's kind of like that. So it's like, okay, an x could be multiplied, so I need an over x. An x plus 1 could be multiplied, I need an over x plus 1. An x plus 1 squared could be multiplied, I need one of those two. So that's kind of what's going on. Now guys, even though I could go about solving by getting all these common denominators, there is a bit of a shortcut to solving now. How do I solve? Divide when improper? Check. Factor the bottom entirely and form partial fractions? Check. If I have, now actually if you go back and look real quick, where are our steps? Do you see right here how they show go up to however high a power you have? So ours, we had x plus 1 squared, so we needed x plus 1 to the 1, x plus 1 to the 2, and that's how high you go. If we had x plus 1 to the 4th, we would have to go up to the 4th and have four different terms. So that's kind of what we're doing with the having the x plus 1 to the 1 and x plus 1 squared. So we formed our partial fractions. Now we need to solve for vars using common denominators. How do I do that? What do I do? Well, it's not bad multiplication, but was there kind of a shortcut to that multiplication? I could do common denominator, common denominator, common denominator, write it all over again, multiply both sides. What's my shortcut?
You just combine.
Multiply both sides by x.
Get rid of this one on the left. And when I multiply to one side, I have to. Does that make sense?
Yeah.
So I'm getting rid of this. Because I don't care so much about the bottom. I need to look at the top because that's where my variables are. So now I have my... This is where you have to be careful on your math. Be careful on the multiplying. Some things are going to cancel. Some things are going to stay. What's going to be left times the a? X plus 1 squared. Does that make sense? The x's cancel, but the x plus 1 squared remains. And then for the b, 1x plus 1 cancels, but x Yeah, you could do x squared plus x, or you could do x times x plus 1. And then for c, the x plus 1 squared, and I have,
CX.
look good? Now what? I hinted yesterday saying we have 3 different coefficients of the x squared term, the x term, and the constant term. So we're going to have 3 different equations. We have to figure out what those equations would be. How do we figure out what those equations would be? We got to simplify. So I'm going to have a, let's see if we can jump a little bit. This is going to be x squared plus 2x plus 1, right? Right? If I square it, x plus 1 times x plus 1. X squared plus 1x plus 1x plus 1.
Yeah.
And then this is going to be, okay, so what do I have? ax squared plus 2ax plus a plus bx squared plus bx plus cx. How can we rearrange stuff in looking at, we want to set something equal to 5 for the x squareds, 20 for the x, and 6 for the numbers. Yeah. A plus b x squared 2a, think, right? 2a plus b, oh, there's another x term, plus cx plus a. Let me pause for just a second, but yeah, and then we can. I totally agree. Oh, those are tied. That's okay. Does that make sense what I did? Take a second. Is that right? Cool. So what's a plus b going to have to equal? Good. Right? So I have a plus b. My 2a plus b plus c. And then my, oh, sweet. I can just back substitute, right?
Wow.
A equals 6, awesome.
B equals 3.
Mm-hmm. So c equals 20 minus b minus 2 times 6 plus 1, 21 minus 12 is 9. Right? Hold on, double check. 2 times 6, 12. 12 minus 1 is 11. 11 subtracted 9. Good? So then, what does that all lead me to? I got it. But now I have to rewrite it, right? Mm-hmm. So I can say, my original function, which, where was he? He was up here somewhere.
A plus the A of x.
Whew. He's a mess. Why don't I just do this and say him. I don't know why all my equations are he's. I apologize if that's offensive. That big old thing at the top is going to be equal to a 6 over x plus b negative 1 over x plus 1 plus c 9 over x plus 1 squared. Am I right?
Yes.
What'd I forget?
Maybe
X plus this whole problem just solved for this piece, right? I need x plus. Does that make sense?
Why isn't it x multiplied?
because this was the remainder, and the remainder
Oh,
is
yeah,
plus
yeah.
how much extra.
I didn't see because the blue circle cut off the.
Oh, yeah. Sorry, my bad. We'll scoot him over.
Alright.
Oops, that just made it worse. I give up. We'll just leave it. Okay.
I should have been able to see.
Yeah, and
There's equation, the a over x and the b over x plus 1.
uh-huh.
So why not is a over x and the second one is b over x plus 1 squared?
Because we split it up into all the possible parts that could combine to be that function. So this one I could do times x plus 1 over x plus 1, and it could be a part as well. So I want to do all of starting at the lowest power, starting at 1, and then building up to, this time it was squared, so I start at 1, I go up to 2. If it was x plus 1, x plus 1, x plus 1, I would have 1, then I'd have squared, then I'd have cubed. You just build up. Because it's possible, as we see, it's possible to have this term as well.
So the first x uses to put 1.
Yeah, but just because that's to the 1, so I just put x to the 1. This is squared, so I do this to the 1 and this squared. So you build up every time. Now, Connor, you said something funny about, wait, what do you do when the squared is stuck inside the parentheses? We'll get to that in a second. Cameron, do you have a question?
So x plus 1 squared is still considered degree 1?
Yes, because the factors are still linear. So like put the two factors together, multiply it's a quadratic, but the factor themselves are linear individually. Does that make sense, Karen? Okay. You guys don't necessarily need to write all of this down, but it is a good recap of the entire process. The steps we wrote before: divide when improper, factor completely, write in terms of partial fractions. That only gets us up to solve. Okay, this gives a little more detail on how to solve, right? Because solve can mean a lot of different things. This is our cool thumb trick that we saw. That's our cool thumb trick, and it says distinct linear factors. That's the exact same thing as saying if they're distinct, then it's not raised to a power. So that's what I was calling non-repeated. That's what I was calling non-repeated, distinct. And then they say for repeated linear factors, they're trying to show you another shortcut. I'm not really sure if it's all that much of a shortcut. It kind of is. I'll see if I can show you maybe the other shortcut they're trying to talk about. Some of these systems can get kind of messy. We haven't really seen them yet in our notes, but I think some of you guys saw them in homework. Some of our equations can get messy. There are some ways to simplify the solving. And to simplify the solving, we can substitute zeros. I'm actually going to erase the thumb trick. Because that is, substituting zeros is kind of what the thumb trick does. But another shortcut for any time you have linear factors is to plug in the zeros after all of this is after multiplying by the common denominator. But before solving the system. After multiplying by the common denominator, but before solving, setting up a system of equations. But and this is really a give or take in a sense of you can take it and use it, or you can leave it and solve the way I've been showing. For quadratic factors, this is basically what you just saw us do. We multiply both sides by the common denominator and then. So this is the steps for solving. Multiply by the common denominator and then expand. So we multiplied everything out. We FOILed the x plus 1. We distributed the x and the x plus 1. We expanded. We multiplied everything to get term plus term plus term plus term. Then we collected terms according to the powers of x. So we had something times x squared. We had something times x. We had just all the non-x, etc. We had the constants. And then take each of those individual coefficients, just like we did, and equate them to the coefficients of the terms on the other side. And I think you guys have a pretty good sense of how to do that. So once again, it's up to you how much you want to write, but I did just kind of want to give you a verbal summary of what we just did over here with multiply by common denominator, expand everything, multiply it all out, collect the x squareds, collect the x's, collect the non-x's. And then you can set up a system and you can solve. For plugging in zeros of factors, let me see if I have an example I can use. That's probably going to be the easiest for you guys to catch on. That's a messy one with the x squared that Connor was saying. Let's do an example right here. What if do I have an example on the next page? Nope. Bummer. I want to show you what this whole, like, you can plug in zeros without the thumb trick, and maybe if it's not non-distinct. Let's just do this. What if I was to give you that's not going to work. Hold on. All right. Let me show you what I mean by plugging in zeros of factors, but not the thumb trick. All right, cool kids. What would you do? We get this problem all zoomed in. What would you do? Divide when improper. Nah. Degree of the top is 0. Degree of the bottom bigger than 0. Okay, now what?
What do you say?
Well, don't worry about the directions. Just what would we naturally do?
Cover up certain parts.
Well, but it's repeated, so I can't cover up parts. I have to form, well, no matter what I do, I have to form, and why am I putting 3? What would the first one be? Uh-huh. And it's just linear, so I'm going to do A. And then the next one? X minus 3 to the first power, but I have to keep on going because now I have x minus 3. Okay. Plugging in zeros of factors happens after removing the denominator. What do I mean by that? How do we remove those denominators, guys?
Multiply by the big denominator.
Good. Get rid of, just get rid of him. It's as easy as that. Just get rid of that denominator. X plus 1 times x minus 3 squared. But when I do on this side, I have to do on this side, right? Okay. So when I distribute, this is going to look a little awkward because he was on the bottom. Let me move him for just a second. You guys already multiplying?
Yeah.
So then what do you get? Let's see. We have 6 equals.
A, x minus 3 plus b, x plus 1.
X minus 3.
Okay. here's what the plugging in zeros means. Guys, can we multiply, combine the x squareds and the x's and the constants? Yes. But there's just a 6 anyway. Really? We have to FOIL all of this and then collect all of it and then write all of it? Here's a shortcut. And sometimes it works nicely and sometimes it's a little bit messier. But the shortcut says, okay, we couldn't do the thumb trick, right? I wish we could have, but we couldn't. Why? Because we have a repeated factor. It's not going to work. Because I would just get, 1 for this one and then 1 for that. Right? We can't differentiate between the two. But what we can do is say, what is a 0? 3 is a 0. Wait, if this equation is true, does it have to be true for 3? Yeah. Why would I strategically plug in 3 to everything?
Gets rid of the x's.
Yeah. What's it going to get rid of? Well, if I plug in 3, then I'm going to end up getting, right, 0, because it's going to be 3 minus 3 squared is 0. Well, 6 is always 6. Plus 0 plus c times 3 plus 1. What just happened? By strategically plugging in the zeros without having to make a system, it's like, sweet, I'm going to get rid of, ha-ha. C is equal to?
6 over 4 is 3 over 4.
Nice. What's another 0 I could plug in?
1 or -1.
Careful, -1, right? If I plug in -1, well, it's not going to be as nice. But what would I get?
16.
Yeah, -1 minus 3, -4 squared, 16a. Be careful of your math. I'm just doing it fast for sake of class. -1, wait a minute. 0, 0. Sweet, right? Because then a equals 16 over 6, which would be 3 over 8. Oh, you're dividing by, I don't know why. I was thinking you were saying 2 over 8, and that didn't make sense. You were totally right. 3 over 8 is great. Haha, I rhymed. We're out of zeros. But we have 2, and we only need a third, right? So when it says up here, it's getting small, I apologize, but it says substitute the zeros, then it says substitute other convenient values of x. What are they saying? They're saying you can plug in c is 3/2, a is 3/8, and then just plug in another random x, an easy one if possible, and then just solve for whatever one variable which will be left, which will be b.
But you only do that when you have an x number on the top, right? With x and a 1?
Well, this is still kind of a long process, but it might be easier than foiling, collecting, system, solve. But sometimes the systems are so easy, it's like, psh, I got this, no problem. Like the last problem, didn't we end up with something that we could just quickly, right? We got a is 6. It was like, boom, like plugging in. But sometimes it might get so messy and you're like, you know what, I just want to plug in zeros and not have to deal with. Guys, what would be another strategic, or what they say, convenient? I know, that's rough. Convenient, really? What's a convenient x to plug in? Maybe 1. I was thinking 0. Because it's easy, but either way. So you could say then for x equals 0. Alright, I have 6. Now, I'm going to have to get rid of all my variables except for the one I need, which is b, right? So I know a. 3/8 times 0 minus 3 squared is 9. See how it's going to be a mess? Plus b times 0 plus 1, 0 minus 3, plus c times 0 plus 1. Now guys, as you can tell, the system would have been bad too, right? You still would have gotten fractions. It's not like our answers are wrong. We end up with I'm going to be a nerd and just say I hate fractions. I don't hate them, but I don't like them, so I'm going to say times 8. Why am I saying times 8? times 8, the 2 and 8 reduced to be 4, that's 12. Times 8, that's going to be 32b, right? No, 24. For some reason I added. Bad. Negative 3 times 8. The 8's cancel. I have 27. Isn't that nicer? You see what I did? I was doing the least common multiple. The 2 and 8 will reduce. The 8 and 8 will reduce. So now I can say 27 minus 12, 15. 48 minus 15, plus 12, good call. 39, my math is not good today. 27, do you ever have those days? Just the math is, the algebra's not working. The addition's not working, oh dear. 39, subtract 39, I end up with 9. So do you see what I mean? It does the same procedure basically, and you're still going to have to kind of go on a hunt, but the zeros can be strategic because you're like, oh, crud, I have to, I don't know, it's just another strategy. And then of course we'd have to go back and rewrite them, but you guys got that. Okay, let's get to that nasty squared in the parenthesis that Connor was talking about before we have to be done. I don't think we're starting 7-5 today. But that's okay with those people gone anyway. Right, the partial fraction, decomposition, cool kids, divide when improper. Do I have to worry about it?
No.
Nah. So what do I start by doing?
Factoring the bar.
Yep. Keep factoring. What do we call that? X squared plus 4. Irreducible. Why? If it was x squared minus 4, it'd be perfect. X plus 2, x minus 2, x squared plus 4. Nothing. So what do I have to do? What would go above as my unknown from x? A. Because the degree of x is 1, this degree is 0. If this degree is 2, what do I need up here? I need a line. I need a degree 1. I need an mx plus b, but I'm going to keep using my letters and do bx plus c. This was from our steps near the beginning of homework where we talked about quadratic factors. That doesn't mean quadratic like it's squared on the outside, but it's a linear on the inside like Cameron asked. It means irreducible quadratic. I can't do anything. I need to have a linear. Why? Because we're looking for partial fractions, and partial fractions are improper. No, sorry, they're proper. Improper we would divide away. They're proper, which means it cannot be equal to the degree, but it can be up to 1 less than. So if it's x, I can have an a. If it's x squared, I can have a line. Danny?
Can I use the rest of it?
Yes, you may.
Thank you.
Then we do the exact same thing. What's the exact same thing? Can't do the thumb trick. I have a quadratic in there.
So you
Kill the denominator. Hey, that's a great idea. I like the verbiage. We're going to kill it, right? Now, but what we do on one side? Right? So, he's dead. I have 3x squared. A, x's cancel. X squared plus 4. Oh, bummer. You see it? Bx plus c is going to have to be times. X squared plus 4 cancel. X is left. Now what? I could be strategic and plug in zeros, but I might, I don't know, it's up to you. I might just set up the system. What do you guys want to do, zeros or the system?
System.
Okay, so the system, I have ax squared plus 4a plus bx squared plus cx. You guys tell me what's next. Good. A plus b, collect the x squared terms. Collect the x term. Collect the non-x term. And then set them equal to I might be able to, but Connor, since I have it in the x squareds and the x's and the non-x's, I don't know if I want to change it. Because I can automatically say what?
Oh, 3x.
A plus B equals 3.
Alright.
Does that make sense?
Yeah.
I have everything I need. C equals, oh, awesome. And then A equals, well, 4A.
So A equals 1.
Does that make sense? Equal,
Yeah.
equal, equal. Awesome. So then I have A equals 1, C equals 4. 3 minus A, 3 minus 1. And then, of course, we should rewrite it, right? So then we would end up with 1 over x plus 2x plus 4 all over x squared plus 4. Now, of course, you could factor out the 2. Back in the book probably would. It's 2 times x plus 2. But either way, you're right. And we're done. Does that make sense?
Yep.
Okay. So what are the funny things? Let's review real quick. The funny things, this is just a trick. The whole zeros thing is just a trick, okay? The funny thing is when you have, like up here, x plus 1 squared right here, I need to do an x plus 1 and an x plus 1 plus squared. And then if it was a cubed, I would do another x plus 1 cubed. I have to build up from the first power. When I have irreducible quadratics, I might have 1, I might have more than 1. How could you know for sure? You could graph it and you could see that, ooh, it's never going to hit the 0. You could do the quadratic formula, you get square root of the negative and say, oh, it'll never have a 0. Or you can just see that it's not possible to factor. I have to make that bx plus c, or if there was another one, dx plus e, fx plus g, stink. The zeros, once again, is just a trick. If you're like, this is going to be a ridiculous system, you could try plugging in zeros, and you might simplify the process a little bit. It might still be messy. Guys, there was one more example, but I think you know what we would do, right? Just real quick for setting up. You would need one of these.
And then x squared plus 3 squared.
Unless, if we multiplied this out, Tristan, that was an interesting idea, the square and the cube, but if I multiplied it out, what would be the degree of the bottom? To the fourth. So he's actually proper. Because we'd have to divide this whole, we'd have to square them. But we would do this, so then, oh my goodness, hello. AX. Ooh, that's a good idea.
You know what I'm saying?
Does that make sense?
Yes.
Woo.
Wait.
Because I would need for the first power, and I would need for the second. Why didn't I factor him? He's irreducible, I can't. So then what would I do?
Just do it.
The same thing we always do. Kill that denominator, right, Tristan? Kill them on both sides, set them up, maybe plugging in a 0, but the sad thing is, are there any zeros for something I can't even factor? No, I can't use that trick. I'm going to have to do it the old-fashioned way. Are we good? I'm good too. 40 seconds to yourselves.
One
Just
of
relax.
those zeros is a maximum.
What are those? Yeah, see, I can't do zeros. So the zeros are a good idea if I can, but I can't always. You guys just chill. I'm just going to kill the denominators. Just for the kiddos who are in student council, just in case. Chapel day. How have you guys been liking chapel?
Actually, I enjoy it.
Good.
I like it. It was a weird concept at first, just because sometimes speakers are hard to get used to.
Yeah.
That's why it's nice to do.
Sometimes it's easy to be distracted too by the he's entertaining, but sometimes I can take away from. But he uses it to try to draw you guys in and then hit you with the word, which is cool. So, all right, cool kids. When it's on the 12, you're good. I'm just gonna play a little bit longer.
Who doesn't know that? Who doesn't know if you lock in the news that you pass out?
I think it was a guy.
Who doesn't know?
Yeah. That's what happened to that freshman yesterday.
Oh, was that it? They locked it.
They
Oh,
locked in
during
their knees
worship.
for worship and passed out.